the integral of 1 over 2 pi, 0 to 2 pi log of 1 minus twice of r times cosine x plus r squared dx, of course, require r bigger than 1. So this Poisson integral, there are many different ways of calculating it. Today I want to use the factorization over the complex number field. And so we're going to prove this lemma first. And z and w are both complex numbers. If z to the power of n is equal to w, and if we write it in polar coordinate form, z and w equal to those equations. And of course, r and r are both positive real numbers. So we can prove that little r is equal to the nth root of big R. At the same time, this angle alpha is equal to beta plus 2k pi over n, where k is equal to 0, 1, 2, all the way up to n minus 1. In other words, there are exactly n different roots. If we consider z as the unknown, we have n different roots for z. W is fixed. So in that way, so first this lemma, right? So which means z to the power of n is equal to r to the power of n according to de Moivre's rule, right? So it times cosine n alpha plus I times sine of n alpha. Right? So it says equal to w, right? W is equal to r times cosine beta plus I times sine beta. Right, since they're equal to each other, so that means r to the power of n equal to r. So that means r should equal to exactly the nth root of big R. Okay? They're both real numbers, so this is safe. So accordingly, n alpha should equal to beta. In fact, n alpha should equal to beta plus 2k pi, because remember, periodic function. Right? So next we're going to determine the restriction of k. Right? So that means alpha is equal to beta plus 2k pi over n. Right? But k cannot go on forever. Right? K may be equal to 0, 1, 0, 1, 2, all the way up to n minus 1. Because if k was equal to n, then what's going to happen is that we're going to have 2 times n times pi, right? Divided by n, that's equal to 2 pi. So again, you have beta plus 2 pi equal to, right, cosine beta plus 2 pi is equal to cosine beta, right? In other words, that's going to be equal to when k is equal to 0, the same situation, right? So 0, 0, exactly, cosine beta plus 0. So again, we only go up until n minus 1, right? Exactly n different possibilities. So that's done. So we're going to use this fact to factorize r to the power of 2n minus 1, right? Let's say if we wanted to, because we're looking for its roots, its zeros, right? If we make it equal to 0, right, then what are the solutions? So in other words, if we want to solve for r to the power of 2n equals 1, right, how to solve it? Right? So using this lemma, I'm going to treat r as z. Of course, this r is different from that r, same as this r. Right? So according to this lemma, z r. Right? First, remember 1 can be written into 1 times cosine 0. Right? Cosine 0 is just 1. Plus I times sine 0, right? Sine 0 is also 0, so this is fine. Right? This is written in polar coordinates. And so, in other words, big R is 1, right? So little r, if I little r, maybe I write it as r naught times cosine alpha plus I sine alpha. Let's find out r naught. So r naught can be treated as this little r, right? This little r. So equal to the nth root of the big R, which is 1. Right, that's 1. And also alpha, the angle, is equal to, here I have 2n, right? There I have n, so this time I should have 2n. And also beta plus 2k pi, beta, this time beta is 0. 0 plus 2k pi, right? So that's equal to k pi over n, where k goes from 0, 1 all the way up to there I go until n minus 1. But here I have the power of 2n, so until 2n minus 1. I have exactly 2n different roots, right? So but I also want to categorize k's. I want to group different k's into different groups. First of all, I want to look at when k is equal to 0 and n, right? If that's the case, then cosine alpha. What's cosine alpha? Right, that's the case. If that's the case, cosine alpha should be equal to cosine 0 and cosine pi. Right? So either it's going to be 1 or minus 1, right? Let's remember that. Later I'm going to use it. And also at the same time, I'm looking at when k is equal to 1 and 2n minus 1. 2 and 2n minus 2. 3 and 2n minus 3. All the way. Looking at n minus 1 and 2n minus n minus 1. Right, that's the case. If 2n minus n, and that's n plus 1. Right? Because I have, that's exactly the same, right? 0, 1, 2, all the way up to 2n minus 1. 0, 1, 2, 3, up to n minus 1 and n. And next is, this one is n plus 1, right? n plus 2, n plus 3, right? This keeps increasing until this number, right? I haven't missed a single one, right? They're all there, right? All here. So the reason I want to group it in this way is that when I look at cosine, let's 1, 2, 3, let's choose any number. Let's say that's k, or that's if that's L, right? So 2L, 2n minus L in general, right? Do they have any relation? So I say cosine when k is, so cosine L pi, over n, right? I also want to look at cosine 2n minus L times k times pi over n, right? Are they equal or are they happen to be opposite? So that's equal to cosine 2 pi, right? 2 pi minus L pi over n. Of course, that's cosine negative L pi over n, because cosine is an even function, so cosine L pi over n, right? So they're the same, right? So symmetrical cosine, right, this and that. For cosine, they're the same, but for sine they may be opposite, because if it's sine get rid of 2 pi, but sine negative, so sine is odd. So for sine, it's going to be opposite, right? So I say if it's sine L pi over n, then it's going to be negative of sine of 2n minus L times pi over n, right? Happens to be opposite sign. So I've just worked out different roots of this equation, right? If I treat r as the unknown, I have exactly 2n different roots, and written as where r can be written as r naught, where r naught is worked out to be just 1. 1 times cosine of alpha is equal to k pi over n, where k goes from 0 all the way up to 2n minus 1. And I have also grouped k into different categories, right? So in this case, let me just write down the unknown. R can be equal to 1 times bracket cosine alpha. So cosine of alpha can be written as k pi over n plus I times sine alpha k pi over n, right? K goes from 0, 1 up to 2n minus 1. So now I can factorize this expression, right, over the complex number field. So in other words, r to the power of 2n minus 1 can now be written into the partial product, finite product, where k goes from 0 all the way up to 2n minus 1, where I have r minus each root, right? And each root is just cosine k pi over n, also minus I times sine k pi over n. Right? Now, like I said, I'm going to separate this finite product into different parts. First, I'm going to isolate this part when k is equal to 0 and n, right? Because respectively, cosine 0, cosine pi, 1, negative 1. Just substitute to that. So that's equal to, first of all, cosine, right? So sine when k is equal to 0 and n, sine 0, sine pi, both 0. So I have r minus 1, r minus 1. So r minus 1, r plus 1. So r square minus 1, isolated out. Okay. Then I go from finite product k goes from 0 to 2n minus 1. It's the same as if, because 0 and n already isolated out, right? I just need to work out 1. But this can be written as, because remember, these are all symmetric for cosine, right? And for sine, they happen to be of opposite sign, right? So instead of going from 1 all the way up to 2n minus 1, I just need to go from 1 up to n minus 1, right? Because I can simply write r minus, because remember, cosine, they are all the same, right? Symmetrical. Right, cosine. All right, for each k here, right? There. Cosine k pi over n. K pi over. First, let me copy down this. I sine k pi over n. Also times r minus cosine k pi over n. Right? Cosine, they're all the same, but sine, they're opposite sign. Mine plus I sine k pi over n. Right? So when k is equal to 1, cosine are the same, sine are opposite sign. Right? K is equal to 2, cosine are the same, sine are opposite sign. Right? Like I said, here each one corresponding to that one, cosine exactly the same. Sine, right, happen to be the negative of that. That's why. So that way I just need to multiply this bracket and that bracket, right? If I treat this as a whole entity, right? Whole entity, then that's minus, that's plus, the difference of perfect square. Right? So r minus cosine k pi over n squared minus I sine k pi over n squared. Right? R squared minus twice of r cosine k pi over n plus cosine squared k pi over n, right? Minus I squared is negative 1. Negative sine squared k pi over n. Right? But that becomes plus. Right? So cosine squared plus sine squared, they just become 1. Now I've successfully factored out the r to the power of 2n minus 1. Now let's look at this definite integral. So this definite integral, I noticed that it's from 0 to 2 pi. So I'm going to break it into 0 to pi plus pi to 2 pi. Right? Because in the end, I want to use a Riemann sum. So I want to see if I can simplify this, see if this is also equal to 0 to pi, hopefully. Right? So if I let x equal to 2 pi minus t, right? Then this part, this I2, right? This I1, I2 is equal to, right? So when x is equal to pi, t is equal to 2 pi minus pi. When x is equal to 2 pi, t is equal to 0. Log 1 minus 2r cosine 2 pi minus t. 2 pi minus t plus r squared dx negative dt. Right. Negative dt. But get rid of negative. Change the boundaries, right? 0 to pi. So 2 pi minus t. Cosine 2 pi minus t. Get rid of 2 pi. Cosine minus t equal to cosine because it's even function, right? Cosine t. Right? Change t into x. Cosine x dx. Exactly the same thing, right? Exactly the same as I1. So, in fact, I is equal to twice of I1. Right. So all I need to work out is work out I1. Right. I1 equal to 0 to pi log 1 minus 2r cosine x plus r squared dx. Right, we're going to partition 0 to pi into n equal parts where each small interval has the width of pi over n. Right? The functional value is taken at the right edge of each small interval. Take the Riemann sum. Right. So I1 is equal to limit as n approaches infinity of pi over n, that's the width of each small interval, times the sum k goes from 1 up to n of log of 1 minus 2r cosine k pi over n. K pi over n. Taken at the right edge of each small interval. Plus r squared. Since I go until n minus 1, maybe I go until n minus 1 and separate the n term. Right? K is equal to n. But when k is equal to n, I have n pi over n. That's cosine pi, constant, right? So that's constant. Distribute pi over n onto this constant, still approaching 0 when n approaches infinity. So that doesn't matter. I just need to work out. K goes from 1 to n minus 1. That's enough. Work out this limit. But using logarithm rule, right? We have a log, then sum them up. Then we can first multiply them together, then take the log. Let's equal lim pi over n, right? Log of the product. Right? K goes from 1 to n minus 1. But this product of this is equal to left-hand side divided by r squared minus 1, right? As I just factorized it. So that's equal to lim n goes to infinity pi over n log of r to the 2n minus 1 over r squared minus 1. Right? Work out this limit. But using Stoll's theorem, right? And we have the n at the bottom as a sequence approaching to infinity. Fine. So, of course, take out pi is constant, doesn't matter. Factor out pi. Right? n minus 1, right? As a sequence, that's bn, that's bn minus 1. Take their difference. Stoll's theorem. And also at the same time, log of this can be written as an minus 1. So log log difference can be written as quotient, then take the log. Right? But r squared minus 1 can be cancelled out. So r to the 2n minus 1 divided by r to the 2n minus 1 minus 1. So according to Stoll's theorem, I've just reached to this part, right? So, and remember, these two integrals are the same. So that's pi. Pi times the bottom becomes 1. Just need to work out log of, then I want to divide everything by r to the power of 2 times n minus 1. Right, so that becomes 1 over r to the power of 2 times n minus 1. Minus 1. No, r to the power of 2 times n minus 1. That will eventually approach 0. Right, but the bottom becomes minus 1 over r to the power of 2 times n minus 1. At the same time, that becomes 1. R to the power of 2n divided r to the power of 2n minus 1. Take the difference of their power because they are on the same base. Right? R to the power of difference of 2n and 2 times n minus 1 is just 2. 2 minus 2n. 2n minus 2n plus 2. That's 2. R to the power of 2. This will eventually approach 0. The r is bigger than 1. So will this one. And this stays, right? Eventually I have pi times log of r squared. Right? Maybe 2 pi log of r. So that's only I1. I1. So I2, as I've proven to be the same as I1, right? So eventually, I should equal to twice of I1, right? Twice of this, 4 times pi log r. So 1 over 2 pi times I, right, should equal to so 1 over 2 pi divided by 2 pi, 2 times log r. Now when r is smaller than -1, I think it's also doable, right? So this will also approach to the same, except we have to put absolute value out here. So when r is bigger than -1, smaller than 1, right? In other words, r absolute value is smaller than 1. In that case, we can easily work out this limit because base is absolute value less than 1, right? N approaches infinity, so this will approach 0. Right? But this is a constant, so log constant. The constant times pi over n still approaching 0. Right? So equal to 0 if r absolute value is less than 1. Right? If r is equal to 1, right, we have log of 1 minus 2 times cosine x plus 1. So 2 minus 2 times cosine x. I think that's also doable. Right, so that's going to eventually turn into right, 0 to 2 pi. Right, that's log of 2 minus 2 cosine x dx, right? So that part can be written as 2 times 1 minus cosine x. Right? I think that's also doable as long as we use double angle formula, right? Turn it into cosine x into 1 minus twice of sine square, half angle, right? Half of x. So that way, 1 and 1 can cancel out. Right? Minus, minus, plus, plus 2 times 2 times 2, 4 sine square. Right? Then take the power 2 down to the front of log. I just need to work out 2 times log of 4 times sine. Right? Sine half x. And also, maybe work out 1 over 2 pi. 0 to 2 pi. 2 times log 4 times sine half x dx. 2 taken out. I think that's also doable. Right. Use log, multiply, right? Product log 4 plus log sine half x. And turn sine into cosine using substitution. Right. Eventually we can work out integral log of cosine half x. Right. But that's a classic integral. I think I've done that before.